Proof by induction number 1 involves series, where we're adding a series of numbers together to get something else, simplified version of it in terms of n. So there's 4 steps involved here. Step 1, we're going to show it's true or prove true for n is equal to 1. So 4 here is the first. So we call it proposition 1 is equal to 4. You can see here, if we put 1 into the right hand side, which we're going to do here, this is the left hand side, the right hand side for proposition 1 is 2 times 1 by 1 plus 1, which is also equal to 4. So therefore you write therefore true for n is equal to 1. Now step 2, we assume true for n is equal to k. We're going to change n to k. So it's true for n is equal to k. Therefore we get our sequence just with k instead of n, or our series 4 plus 8 plus 12 plus 4k is equal to 2k by k plus 1. And that brings us to step 3. We're going to prove true for n is equal to k plus 1. So the k plus 1 is the next term in the sequence, so the one after this one. So that would mean that 4 plus 8 plus 12 plus 4k plus the next term is 4 times k plus 1. So if k is 10 in here, the 10th term is going to be 11 in here. Is that equal to when we put k plus 1 in for k on the right hand side? So we're going to manipulate the left hand side. So you can see here this k becomes k plus 1 and I've still got the plus 1 after it. So this simplifies to be 2 by k plus 1 by k plus 2. So let's go and look at the left hand side now so you can get it into the same as the right hand side. So we've assumed, and we're always going to use our assumption to bring down, we've assumed that up to this point this is all equal to 2k by k plus 1. So therefore the left hand side is equal to 2k by k plus 1, and adding this term to it, plus 4 times k plus 1, will that give me this right hand side over here? So let's have a look. This works out to be 2k squared plus 2k plus 4k plus 4. Bringing like terms together, we're going to get 2k squared plus 6k plus 4. You can see we need this 2 in front, so if I factor out my 2, I'm going to get 2 times k squared plus 3k plus 2, which works out to be 2 times k plus 1 by k plus 2, which you can see is equal to the right hand side. So we finish off by saying therefore true for n is equal to k plus 1. So proposition k plus 1, this doesn't have to be exact, but something along these lines is true. So we normally finish off by saying proposition 1 is true, proposition k assumed to be true, proposition k plus 1 by induction shown to be true or proven to be true. Therefore proposition n is true for all n is an element of natural numbers. And there's a few different ways to finish these off. You may say you're written slightly different elsewhere, but this is the first example of proof by induction of series. The maths involved is not difficult. Just learn off the process, practice 5, 6, 7 of these, and you should master this skill. In this example, we're going to prove by induction for all n is an element of natural numbers. That's 7 plus 7 squared plus 7 cubed plus all the way to 7 to the power of n is equal to 7 over 6 times 7 to the power of n minus 1. So proposition 1 is my 7, is my left hand side. Is that equal to 7 over 6 by 7 to the power of 1 minus 1? So this is going to be 7 over 6 by 6, which is equal to 7. Therefore, true for proposition 1. So we're going to assume true for n is equal to k. Therefore, we get 7 plus 7 squared plus 7 cubed plus all the way to 7 to the power of k is equal to 7 over 6 times 7 to the power of k minus 1. And this is the assumption that we're going to bring down in a minute. So let's prove true for n is equal to k plus 1. So we're going to show 7 plus 7 squared plus 7 cubed plus 7 to the power of k in the next term, 7 to the power of k plus 1 would have to be equal to 7 over 6, and k gets replaced by k plus 1 times 7 to the power of k plus 1 minus 1. So if we bring the assumption down, we're assuming that this guy is equal to this guy, so that includes all of them. So we can say that 7 over 6 to the power of times 7 to the power of k minus 1 plus 7 to the power of k plus 1 will have to be equal to this right hand side here. So multiplying 7 over 6 by 7 to the power of k, you can see what's going to happen here. This is going to become 7 to the power of k plus 1 over 6. And we have minus 1 times 7 over 6, which is minus 7 over 6 plus 7 to the power of k plus 1. Now I can do this a couple of different ways. I'll just bring my minus 7 over 6 down and my 7 to the power of k plus 1. So we have a 7 to the power of k plus 1 here and in here. So if I factor that out, 7 to the power of k plus 1, that's going to leave me with 1 over 6 to get the first term, and it's going to leave me with plus 1 to get the second term. And I have my minus 7 over 6. So inside the bracket here, you can see we're going to get this 7 over 6 that we're looking for. So we have 7 over 6 by 7 to the power of k plus 1. And this is also 7 over 6, so I can factor out a 1 there, minus 1. So we end up with 7 over 6 times 7 to the power of k plus 1 minus 1, which you can see is what we were looking for. Therefore, equals right hand side. So true for n is equal to k plus 1. P1 is true. Pk, assume true. Pk plus 1, proven to be true. Therefore, true for all n is an element of natural numbers. So that's all you need at the end of these questions. We'll do one more and then you guys can go and practice some of these questions. So prove by induction for all n's an element of natural numbers. That's 7 plus 9 plus 11 plus 2n plus 5 being the n term is equal to n squared plus 6n. So what about if n is equal to 1, or proposition 1, you can call it either. It's my first term, which is 7. We can see here that 1 squared plus 6 times 1 equals 7. So left hand side equals right hand side. You don't have to write this, but no harm to just expand it out a little bit. Proposition k, assume true. You do need to write assume true. Therefore 7 plus 9 plus 11 plus 2 times k plus 5 is equal to k squared plus 6n. Proposition k plus 1 to be proven. I'm just changing the writing a little bit so you can see that it's not prescriptive, just needs to follow a certain pattern. Therefore 7 plus 9 plus 11. Should have put plus in here, plus 2k plus 5. And the next term is when we replace k with k plus 1, so 2 times k plus 1 plus 5. And I just need a bit more room here, and that's equal to k plus 1. I had an n there instead of k plus 1 to be squared, plus 6 times k plus 1. So if I pause, the right hand side becomes k squared plus 8k plus 7. The left hand side now we need to show is equal to that. So I have my assumption, which is all of this guy. So we can say up to this point, we can say that that's going to be k squared plus 6k. So this is my left hand side. Plus, in the bracket here we have 2k plus 2 plus 5. So we have k squared plus 6k plus 2k plus 7, which is k squared plus 6k plus 8k plus 7, which is equal to the right hand side. So proposition k plus 1 is true. We could also say also p1 is true. pk assumed true. So true for all n is an element of natural numbers. So 3 examples here in proof by induction for a series. We'll go on next to look at proof by induction for divisibility, and then after that inequality. So practice some more questions in this topic before moving on.